Greetings, Mr. Johnny. Sorry about that. Yesterday, the bell interrupted us abruptly, out of nowhere, so we had to conclude those notes. Well, today will be your actual, for real, last day of catching up on material. So yesterday I kind of introduced you to the concept of acids and bases and how there's, different theories. And then I kind of talked about the pH scale and talked about different indicators and how there was these different equations that you could use to figure out the pH or pOH of a solution. And then I worked through one example problem. Well, today I'm going to actually just work through 3 example problems, and that'll be it. Try and be as quick and efficient as possible, so let's get this started right away. Question 2. 1.5 liters of 0.510 molarity hydrobromic acid is mixed with 0.80 liters of 0.480 molarity strontium hydroxide. What is the pH of the resulting solution? So as you can see, I wrote out the chemical equation for this question. Very necessary to get that written out. And then I wrote in the key information below hydrobromic acid as well as strontium hydroxide. Okay. So first things first, when we want to solve this question, let's figure out the concentration of hydronium within each of the reactants here. So let's find the concentration of hydronium in, what should we start with? Let's start with hydrobromic acid, because I'm right there. So to figure out concentration, as you know, it equals moles per liter. So in this case, we want to take the liters, we want to add the total volume of both of these reactants to get the total liters. 1.5 plus 0.8 is 2.3 liters. Now there's 1.5 of those liters are from hydrobromic acid, right? So when put 1.5 liters up there, that will give us the decimal of how much of the reactants is hydrobromic acid. But to figure out concentration, we will need to figure out the moles as well, because concentration, if you know, is N over V. N equals moles and V equals volume, right? So the top, and of course moles is concentration times volume. So on the top, we have our volume, but we need to multiply it by the concentration of hydrobromic acid, which is 0.510 m times that. So 0.510 m times 1.5 liters. I know I don't really have space there, but that's what the calculation is. All over 2.3 liters. That should give us concentration of 0.3326 molarity. We want to get this to as many decimals as possible, so that, because we don't want to do too many rounding, because there might be more answers using this value at the end. So we want it to be as specific as possible. So that's our concentration of hydrobromic acid in terms of hydronium. Next, we'll do the exact same thing for the strontium hydroxide. So strontium hydroxide, since this is actually a base, we'll be doing it with OH minus instead. Before we were doing it with H3O or H plus. With strontium hydroxide, because it's a strong base, we'll be using OH instead, because it'll be easier. Okay, this time we got... Oh, quick note, by the way. Since in the chemical equation we have a subscript of 2, we're actually going to multiply the concentration of 0.480 by 2. So times 2 equals 0.960 m. Because there's actually 2 hydroxides per 1 strontium. So now we take exact same thing as last question, 0.960 m, and we know there's 2.3 liters, and then the liters of strontium hydroxide is 0.80, of course. perform this into our calculator, we should get 0.3339 m. Okay, so we have these two concentrations. 0.3326 and 0.3339. Okay, so let's figure out the amount that's left over. Which number here is larger? So we have 0.3339 and 0.3326. Well, I actually lined this up perfectly. 0.3339 is larger than 0.3326, so let's subtract these. So we subtract those to get the concentration of OH left over, because there is more hydroxide than hydronium, so this will tell us how much, because again, this neutralizes, so this will give us the hydroxide that's left over after. Okay, so essentially this is hydronium and this is hydroxide. 0.3326 molarity of the hydroxide will react with that, and it will cancel out, and then we'll have some amount of OH still remaining. So we'll subtract those numbers. So OH minus equals, take those two molarities, subtract them, gives us 0.0013 m of the concentration of hydroxide. And now we're trying to figure out pH, but we have the concentration of hydroxide. So I showed you some formulas earlier in the previous day. If we have the concentration of hydroxide, we can figure out the pOH. And then we can use pOH to go to pH. So let's do that right now. Okay, so we have our number, and then we would take pOH equals negative log, and then we take that number, 0.0013. Okay, so we have that number, and that will give us 2.89. That's our pOH, not our pH, and we know pH plus pOH equals 14. So if we have 2.89 is the pOH, we just do that, subtract 2.89 from both sides, 2.89, and it'll give us a pH value of 11.11. There you go. That's that. Second question. Now, if you remember from chemical equilibrium, ice tables, well, they're making a return here in the acids and bases unit. Okay, let's write down our equation. So CH3COOH is acetic acid. Of course, that's going to react with water. And this, since it's a weak acid, it will be an equilibrium reaction. So this water will, of course, become H3O+, and then the acetic acid will lose a hydrogen to become CH3COO-. So we make a nice table here. Initial change, and then equilibrium. So let's do that. Yeah, okay. So our initial concentration is 0.10 for acetic acid. For water, we actually just put Na. So whenever you're dealing with ice tables in this unit, whenever you have water, it's always going to be Na. Because, Johnny, because water is a liquid at this temperature, because it's assumed room temperature. Yes, that is correct. It's assumed to be at room temperature. Okay, and of course these concentrations will be 0. Because this is at the start of the reaction. Equilibrium, they'd have their own concentrations, but we assume this starts at the beginning. Okay, so notice there's no coefficients that are greater than 1, or that are not 1, they're all 1. So therefore we know the change in concentration, because this is going to lose some, will be minus x, and these will each gain an x, because the coefficients are 1. Okay, so for this question, you need to figure out the Ka value, which is kind of like the equilibrium constant. If you do not have a data booklet for chemistry, you might be able to look this up online. I will provide you with any data booklets on tests, of course. But if not, like in the future, I mean, actually, I'm sure you'd have a data booklet for any tests, but if you're ever doing homework, you can always look it up online. So, of course, acetic acid, let's just find it. Where is it? Oh, okay, there you go. The Ka value is 1.8. Did I say A? That's funny. 1.8 times 10 to the power of negative 5. Okay, so actually, let's just finish this. So 0.10 minus x, and of course this will be x and x. So we have 1.8 times 10 to the power of 5 will equal, and again, remember we take the concentrations of our products and then divide them by the concentrations of the reactants. So x times x, let's multiply this to become x squared, over, since water is liquid, we don't count it, over 0.10 minus x. And of course, the rest is just simple algebra. Okay? So, in this case, actually one thing, although it is not required, you are able to use the quadratic formula to solve this. However, I will not require you to use a quadratic formula to solve it. And the reason is because the x value is such a small number. In this case, oh, my mistake, actually. This is supposed to be negative 5. 1.8 times 10 to the power of negative 5. My mistake there. And that's exactly the reason why I'm not requiring you to use the quadratic formula. Because our Ka value is such a small number, a single x will not significantly alter our final answer. It'll affect maybe the third or fourth decimal place, maybe second. It really depends on how small or how big the Ka value is. If the Ka value is larger, when you get to stronger acids, you might want to use a quadratic formula. But when we're dealing with a quite weak acid, the x shouldn't affect the value too much, or our answer in a major way. So with that in mind, you can assume 0.10 minus x is approximately, that means approximately 0.10, because the x value is so small. So that can be rewritten as 1.8 times 10 to the negative 5 equals x squared over 0.10. Of course, you can use a quadratic formula if you so choose to. It is possible you would get two answers, and you'd have to kind of figure out what it is. And it is a long process typing that all into your calculator. Or if you don't have a calculator, you could solve it by hand, but that would take even longer. And it could be an irrational number. So that's why I say, when we're dealing with small Ka values, such as 1.8 times 10 to the power of negative 5, you are able to just assume that the denominator is just the original concentration. Okay, so the rest of it becomes pretty simple, of course. What should we do here? Let's see. Okay, so what should we do? We can multiply both sides by 0.10. Okay, so let's multiply both sides by 0.10. Those will cancel, of course. What will this give us? Actually, you know what we can do? We can actually just take the square. Yeah, okay. So 1.8 times 10 to the power of negative 5 equals 1.8 times 10 to the negative 5 times 0.10 equals, what does that equal? 1.8 times 10 to the negative 6. Okay, 1.8 times 10 to the negative 6 equals x squared. And now we can take the square root of both sides. So x equals square root of 1.8 times 10 to the negative 6 times 10 to the power of negative 6. And that will give us an approximate value of 1.34 4 times 10 to the power of negative 3. So we're trying to find the pH here. So now we have the x value. We can plug this value into there. And then we'll have, actually, since we now have, because we're trying to figure out the pH, we can just take, again, if we relook at the equation, pH equals the antilog of concentration of hydronium. In this case, the concentration of hydronium is in the products, so we can take the antilog of x. Okay, so let's take this number. I'm just moving it here. Okay, so pH equals minus log 1.34 times 10 to the power of negative 3. Okay, and that should give us a pH of approximately 2.89. And that is your final answer. Just quick note, in terms of sig figs with pH, we only consider places to the right of the decimal significant with pH. In the original question, we had 2 sig figs here. And pH, although there's 3, what would be typical significant figures, we don't include the 2. So we would also just have 2.89. Okay, that's the second question. Last question before you can be on your way, Johnny. This was the last question that you missed. Okay, let's see. So a solution of iron 3 bromide has a pH of 3.850. What was the initial concentration of the solution? Okay, so this is probably the hardest question of all of them here. First things first, let's start with writing our equation down. So Fe H2O 6 plus H2O, which, like last question, we do not include in our calculations. This becomes Fe H2O5 H2O5OH and then plus H3O plus. Okay. So let's do our ice table again. So ice. You never get away from those ice tables. Okay. So we're trying to find out the initial concentration. Before we knew it, and we're trying to find the pH. But this time we're given the pH and we're trying to find the initial concentration. So we're going to give that X. This is Na all around. Doesn't matter, right? Because it's a liquid. Water is. So we know X. Of course, these are 0 because this is an initial concentration and hasn't yet reached equilibrium, because remember the E in the ice table stands for equilibrium. And 0, okay, we can't figure out the rest of this table. But we have the pH. So to figure out the concentration of hydronium, we can simply take 10 to the power of negative pH. Right here, concentration of hydronium, 10 to the power of the negative pH. So we can take that and figure out the concentration of hydronium. So we have a pH of 3.850, and remember it's 10 to the negative 3.850. That'll give us the concentration of hydronium right there. So if you do that calculation, it should give you 1.413 times 10 to the power of negative 4, and that's our concentration of hydronium. And we can fill that in. Of course, in this question, you notice the coefficients are also 0. So in this case, at equilibrium, 1.413 times 10 to the negative 4, also a coefficient of 1, so this would also be 1.413 times 10 to the negative 4. Change would just be plus this amount, and that's the ice table. Oh, and actually this would be X minus 1.413 times 10 to the power of negative 4. Okay. So now we've completed the ice table, and now we're essentially just trying to figure out our X value in this case. So if we look at our relative strengths of Bronsted-Lowry acids and bases, Let's find this right here. Iron 6.0 times 10 to the power of negative 3. Okay. So we have the Ka of 6.0 times 10 to the power of negative 3 equals, since we're multiplying this, we take the products and then divide them by the reactants. This can, because these are the same, we can just write this as this number squared, right? Because there's two of them to save us space, right? So we can take that and put 1.413 times 10 to the power of negative 4 all squared. And then that is over x minus 1.413 times 10 to the negative 4. And that is our calculation in this case. And the remainder is just using algebra to solve for the rest. So in this case, what can we do here? Let's see. Well, we could actually just swap these values, the denominator and that. Okay, let's do that. So we have 1.413 times 10 to the negative 4, all that's squared, of course. And let's divide that by 6.0 times 10 to the power of negative 3. Okay, and then of course we would have x minus 1.413 times 10 to the negative 4. Now we can add this to both sides. So we have x equals this plus that, of course. So if we plug this into our calculators, this fraction, and then adding that number, we will get an x value of approximately 1.446 times 10 to the power of negative 4. Now, in this case, I didn't actually show the math, but I mean, I assume you're in pre-calculus, Johnny. I mean, this is basic algebra, technically. But to solve for x, you can multiply both sides by the denominator to cancel it out. That's what I did. I didn't show it there, but I assumed you already knew that. But yeah, so now we have the x value. And in fact, that is actually the answer, because we don't have to do any more. X equals, so the concentration of FeH2O 6 equals 1.446 times 10 to the negative 4 m. That's our final answer, because on the ICE table, the initial concentration was just X. And that's it. There are the 3 problems that we did. Wow. That took over 20 minutes. It's a lot of work. I kind of went through it. But in reality, the questions aren't actually that bad or overwhelming at all. Honestly, a lot of it is just basic algebra and the ability to read from the data table. You do not have to use the quadratic formula for any of the questions that I will give you. Future teachers might, but if so, all it is plugging numbers into the formula, which isn't, terrible. It can take a lot of work though, but of course I will not require that. So that's it. You're caught up, Johnny. You're caught up. You know what? You better not fall asleep in class again. You know what? Although I loved and enjoyed teaching you again, I'll admit, I do not want to do this for the rest of the year. There's so much that we cover in these classes these days. I can't afford you falling asleep in class. Now guess what? You're going to get a test tomorrow, Johnny. Be prepared. Take care, though. Have fun in your next class.